All right, we're going to go through the valid tic-tac-toe state problem. This solution isn't necessarily the most efficient or the least lines of code. It's meant to explain the process in the simplest way possible. I use long variable names to make sure that we understand what is going on at each stage. So let's get started. The instructions say that we're given a board. It's 3 by 3 and it has 3 possible characters. There's the space, which means nobody has played, the X, which means the X has played, and the O, which means the O has played. Players can take turns placing their characters into empty squares, the ones with the spaces. The X always goes first, and the second player is always O. So we know that X will always start first. So then they place X's and O's into empty squares. They never put it into filled ones, pretty straightforward. And the game ends when there are 3 of the same non-empty characters filling any row, column, or diagonal. We've got 2 diagonals. And no more moves can be played if the game is over, which means all the squares are filled or somebody won. So they give 3 examples. The first one, there's an O. This can't happen because player X always goes first. Now we have this other one. Well, we have X's, we have O's, we seem to have more X's than O's, but this still isn't valid because now there are 2 more X's than O's. So let's just simulate a game. X goes first, great. O goes second, great. X goes third, great. But now we need an O instead we have an X. So this is an invalid state. So we might want to take note of that. And finally, we have this board right here. So let's just play a game again. X, O, X, O, X, O, X, O. That seems to be correct. All right, so how do we approach solving this problem? Well, we have our main function, valid tic-tac-toe, and it's given a board. We're not going to play the game to the end like other problems. We're just going to see whether it was possible to get to this state. So how we do this is, first of all, we want to check if there's a winner. So we want to check if X is the winner, if O is the winner. If both X and O are the winners, that's not good. If one of these guys is a winner, then we want to check those ratios that we went over before. So let's see how it works to check for the winner. And this is something that you will probably use for a lot of tic-tac-toe problems and similar array, multi-dimensional array traversal problems. So first we want to check columns and rows, and then we want to check diagonals. How we do this is we have a nested for loop right here. First we have I, which represents the first dimension, and then we have J, which represents the second dimension. But here's a really cool trick we do. We can flip the I and the J for columns and for rows. So in the same for loop, we can be checking whether a row wins and whether a column wins with that same index. So let me just draw out how that looks like. I have X, 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 O, 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 O. So if I is equal to 0, sorry about this, 0, 1, 2, 2, 0, 1, 2. So this is I, and these are J for now. So the first configuration is going to be checking for rows. These guys are I rows. So 0, 0, 0 is the I, 0 is the J. It's going to be an X. Okay, sounds good. We're going to check that against the player. So we are asking, did X win? All right, X, so far so good. Now we're going to check 0, 1. That's an X. Yeah, so far so good. We've got another X. And then we've got 0 and 2, which is also an X. So what happens here? In this condition, we say only if this cell is not equal to a player, we will mark row win as false. Otherwise, we assume that they won. So, you know, if this was an O, so let's say we're checking the second row. So we check 1, 0, and that's an X, so far so good. 1, 1, which is an O, that's not good. So as soon as we hit that first O, we say row win is equal to false. All right, so we know that row win is equal to true. That's good. Now let's see if the column wins. So we have a row win, that's fine, but just for simplicity, I'm going to also check if the column wins. There's probably a better way to optimize it. So what we do here, this used to be our I, now this becomes our J, and this becomes our I. So I is equal to 0, J is equal to 0, and the first we have is X. Great. I is equal to 0, J is equal to 1. It's X, still good. I is equal to 0, J is equal to 2, that's an O. We flip the column flag to false. So after we finish up this for loop, so this for loop is going through all the rows, all the columns, it's only going through the first row and the first column. As soon as we check the first row and the first column, if there's a win in either the row or the column, we return true. And then we move on to the second row and the second column. That is controlled by this line 63, which is the external loop. So the internal loop is controlling just one column, just one row at a time. Okay, and we exit early because we don't want to check every single row. But we forgot to check the diagonals. No worries, we just have another loop. This is a one-dimensional, just a n complexity loop. It's not nested. And it's pretty easy to check. We just go through all the i's, 0, 1, 2, and we say, okay, if I, that's 0, 0, is not equal to the player, so the same logic, X, so far so good. Then we move on to I is equal to 1. So 1, 1, that's an O. Okay, that diagonal lost. Now we have the second diagonal, which starts from the right. So that's board size 3 minus 1, which is 2 minus 1, minus I, which is still 2. So we check index 2, row 0. 0 is I, which is the row, and this second part is the column, which is 2. So that's going to be X, so far so good. Then if we move one down, I becomes 1, and then J is equal to 3 minus 1 minus 1, which is the I, which is 1. So that's going to be this O right here. And finally, we have I equals 2, 3 minus 1 minus 2 is equal to 0. So that is going to be row 2, column 0, O. So X, O, O, that is clearly not the winner, but that's okay because we already know that we won thanks to the row, specifically row 0 right here. All right, so we know that X won. That's great. So we return that here. Now we do the same thing for O. So why didn't we just check for both X and O in the same loop? Well, it's because it's possible that both X and O won. And I think it is possible to check for both X and O in the same loops, but again, this solution is more geared towards simplicity, easy to understand. So we're just going to check for the winner for each of these players. So I don't have to really go through what this looks like for O. It's exactly the same as for X. But let's say that X was the winner and O is not the winner. That's great. That seems valid so far. If X and O are the winners, that is not valid. If neither X nor O were the winners, that's also perfectly fine. So now we move on to validating those ratios, which is that final step. And what we do is we pass the board, and then we pass who the winners were. So let's go into that function. So we want to validate those rules that we talked about. First of all, if both of these guys are winners, that is not a valid state. Now we want to validate the ratio. Remember what we said, that there has to be either the same amount of X's and O's or one more X. But it gets a little bit more tricky than that. If the winner is X, then we'll always have one more X because it's X, O, X, O, sorry. Yeah, X, O, X, O, X, O, X, O. So far, nobody won. But if the X goes here, we have one more X. We also can't have the situation where, we can't have the situation where there is one more O, like this guy. We can't have the situation where there's two more X's. So what are the rules here? Well, first of all, we want to count those X's and O's. Pretty simple. We just have that nested for loop, counting X's, counting O's. And then we check the rules of the game. If X wins, there should be one more X than O. So winner's X, then it's one more than O. If winner is O, they will be the same amount. And finally, if nobody won, then these guys could either be the same or there could be one more X. So those are pretty much all the rules. And when we run this, it should work. It's not the most efficient solution, but this should be one of the easiest to understand solutions. That's all.